Hey, Laura, can you hear us?
Yeah, I can hear you.
Okay, good. All right, we'll just wait. So I think I can see your stuff and the screen too. We'll start soon. Thank you.
Hey.
All right.
Let me try and screen share.
Okay. So the committee is here. So just a brief introduction. Remote. We have Professor Anike Berra from Purdue University, who is also a former Gamma member. And we have Professor Dinesh Manocha, who's on travel today. Right here, we have Professor Tom Goldstein and also Professor Mumu Su and Professor An Lee. It's a tremendous pleasure to have all of you here. And also it's a tremendous pleasure for me, who have worked with Laura since like 2018, 2019, as an undergrad right here. And we have been working together for more than 6+ years. I cannot tell you how proud I am of her. She has done a tremendous amount of work. And, she is also not just great at doing research. She has been very nurturing and help advising several master and currently one REU students in college and one high school students. And she continued to do her research and defending and traveling and conferencing just like everybody else. I just want to say a couple of honors she has is the Maryland Transportation Institute Fellowship. And also she was selected as the future leader by the Maryland Robotics Center and the only one from Maryland. All the others are from top program in the country. Okay, Laura, please go ahead.
Yeah, thank you so much for the introduction. So hi, everyone. Welcome to my defense. And my thesis is titled Modeling Traffic Dynamics, Human Factors, and Sensitivity for Generalization in Autonomous Driving. So I would like to thank my advisor for being here, Professor Lin, and as well as my committee members and my dean's rep. So just a motivating example. If you can imagine, it's a beautiful day and Tiffany is riding an autonomous Tesmo southbound on Route 1 towards the UMD campus, and we are approaching an immediate merge lane from 193. And she goes, wow, I cannot wait to ride this autonomous vehicle Tesmo to visit the University of Maryland College Park. She's so excited. And she sees on the right side, oh, here comes a Maryland college student driver. I hope they know proper right-of-way traffic rules and look before merging into oncoming traffic. And they see this person inching up. Then she goes, all good. Any in-distribution driver would have seen us by now, so this driver must just be inching forward. But then a crash happens, and she goes, well, if only this autonomous vehicle's policy accounted for rule-based traffic systems, edge case driving styles, and had a framework for detecting sensitive data during training. So thank you so much to my friend Tiffany for modeling for this. And actually, this is a sneak peek. So this is actually a merging pre-crash scenario from a virtual reality simulator that I was involved with developing during my thesis work. So just to jump right in to motivating the thesis. So there's several challenges in practical autonomous driving. So for example, rainy weather, complicated roads, and left-handed driving are things that we don't typically see as drivers from Maryland ourselves. But the typical approach to these is just to collect more data. We just scale, essentially. But what happens in the case that we have car accidents? Or this is easy, obviously, scaling, but what happens when we have car accidents? Is the solution genuinely just to collect more data on car accidents and then find ways to generalize to the real world data? So this becomes a little more challenging than just scaling. And so the question is whether scale is really all we need in this case. So for a lot of edge cases, large scale data collection is not feasible. And some things are out of our control, like adverse weather, poor sensor quality, especially if you have like crowdsourced data. And also we have edge cases in terms of pairwise interactions between agents. So this also is like spawning from behavior. And then also, like I mentioned in the last slide, we have the possibility of accidents. It's expensive to collect them in controlled environments, and it's also just not feasible to wait for them to happen in the real world. So this ends up being a lot of data to scale. And also for generalization, we need a lot of diverse variations of this data. And then another problem is that human behavior is not interpretable. And so if we can't observe it and we can't measure it, how do we collect data on it? How do we ensure that we have even like a good set of human behavior? And so one thing I want to point out is that traffic dynamics are rigid. So for traffic modeling, for rule-based modeling, there's typically high-level and low-level ways of modeling traffic. And the high-level way describes the traffic system as a whole. And so there's two types of models, two main types, and then there's hybrid between the two. But the two main types is macroscopic. An example is All-Rascal-Zhang. And it treats traffic like a fluid. So they typically use like partial differential equations to model these. And there's no notion of like individual vehicles in these models. And then you also have microscopic or agent-based models, like the intelligent driver model. And this describes the acceleration of individual vehicles with respect to the vehicles in front. So they're also called car following models. And then you have low-level vehicle dynamics. So this is like the classic navigation robotics problems, like how many degrees of freedom do we have in a vehicle, and what's the reachable workspace? And the very obvious observation is that some predicted trajectories may not even be physically feasible in a lot of deep learning problems. But the observation here is that traffic dynamics are rigid and describe traffic systems well enough without these million parameter neural networks. And the other observation is that human behavior is uninterpretable. So there's this notion of mixed autonomy. And mixed autonomy is essentially the scenario where traffic is partially human-driven and also partially automated. So you can, for an example is like if the road, 20% of the vehicles are autonomous and 80% are human-operated. And this is a bit futuristic for now. We don't really see autonomous vehicles in College Park. But this is becoming an imminent problem. There's big cities that are trying to scale up autonomous vehicle with rideshare and stuff like that. So this is definitely a problem that we need to have on our horizon. And a very obvious challenge with this is that we don't know how people behave around autonomous vehicles yet. There's this trust factor. People aren't quite sure about how much they trust autonomous vehicles, especially when it comes to handling difficult decisions. And then we know even less about how other drivers interact or how they'll behave around autonomous vehicles if they perceive it to be autonomous. And behavior is really variable with respect to location and where you learn to drive. So like one very basic example is drivers in Maryland will drive differently from drivers in North Carolina. And so behavior is somewhat abstract and difficult to define. So this is another observation. And then basically, the motivation of the thesis is that modeling traffic dynamics, so the rigid portion, and human behavior, which is more abstract and fuzzy, can help in edge cases specifically. And so the edge cases that we're talking about in particular are degraded visibility, like adverse weather, sensor noise, or occlusions, and anomalous or high-risk scenarios. So this includes like pedestrian and animal crossing, closures from bicycle races and stuff like that, or unique construction patterns. And also edge case behavior, like overly aggressive, overly anxious, or unpredictable drivers. So these are just some examples of what we would think of as edge cases. And so this brings me to my thesis statement, which is that combining differentiable traffic dynamics, human behavior priors, and visual perception robustness with deep learning can not only provide improved performance in general cases, but also improve interpretability, data efficiency, and robustness on rare or unoptimal cases. So this thesis is split into 3 parts. And throughout this presentation, I've kind of color-coded them to be red, blue, and purple. So for the first part, it's more focused on the rigid concepts of traffic and vehicle dynamics. And then the second part will be focused on human factor studies. So these are non-rigid concepts that are kind of abstract, hard to interpret. And then the last part will be on analyzing sensitivity to natural corruptions, which is more focused on perception. So here is the research roadmap visualized, and each part that I'll go through in this presentation. And so each box is a project that I'll discuss, and they're color-coded by which part they belong to within the thesis. So right now, I'm just going to go into the first work, which is modeling high-level traffic dynamics and autonomous driving. And the motivating question here is, how do we apply high-level traffic flow dynamics to autonomous driving policies? So just imagine we have this autonomous vehicle on the road, and we ask whether this vehicle can drive in a way that can minimize everyone's braking on the highway. And so the main goal of this work is to be able to find this relationship between the dash cam view and the actual traffic state. So the traffic state involves like the positions of each vehicle and the road lines and the conditions, the state of the traffic lights, things like that. So can we find this relationship and then take advantage of, for example, high-level traffic flow dynamics to optimize this autonomous driving policy? And so this is the first project that I'll be presenting here, which is traffic-aware autonomous driving with differentiable traffic sim. And this was presented at 2023 ICRA. So our proposed solution for this is to basically separate the learning of controls into acceleration and everything else. And so typically for end-to-end driving, a lot of the state-of-the-art models use joint learning of control. So they learn steering and acceleration jointly. But in our what we propose here is that we kind of separate them. So basically, the idea is that if we learn from offline data, which is what we consider to be expert data, the possibility is that our expert data is probably from humans, and we don't know if humans necessarily drive optimally to reduce congestion, because it is like a human-created problem. So what we do is we create this co-simulated environment between Carla and Sumo. And Carla is basically just like this driving test bed. So it looks like a game engine. It's built in Unreal. And we can get all these dash cam views from actually driving the vehicle through the sim. And then Sumo, you can think of it as like a high-level traffic sim. Like you can see the bird's eye view. It gives you the traffic flow information, fuel consumption, things like that. And it's much more on the level of traffic state. So we co-simulate these. And the main idea is that the expert or privileged agent provides optimal steering control in this step, so we don't worry about things like steering. And then the acceleration agent just focuses on how to accelerate optimally. And so here's kind of an example of what Carla and Sumo look like. And we essentially we collect data that pairs these two simulators together. And then in phase 2, we basically just learn everything else. So now in this one, the acceleration agent basically supervises, acts as the acceleration expert for supervision of the policy, which is in the solid blue box on the bottom. And the steering prediction is supervised by just the offline data. So like in the previous step, we used an expert that had privileged access to information from the simulator. In this one, we just use offline data that could be collected from like a human, for example, but acceleration is handled by the expert, the acceleration expert. If you notice, phase 1 is more or less trained with reinforcement learning, and a problem that we encountered is that like simulation between Carla and Sumo is kind of slow. So we want to improve sample efficiency, and a perfect way to do that is with traffic gradients. So what is a traffic gradient? It's basically just a derivative of the current traffic state with respect to the last state. And it describes traffic dynamics according to car fouling model. So if you recall, there's different ways of modeling traffic. We're talking about the agent-based or microscopic model, also known as car fouling model. So we use IDM in this case. And we augment the experience buffer that's collected by the model in phase 1 using the gradient of the reward with respect to the action. And this is very direct because ODEs are naturally differentiable, and we basically just have to find the analytical gradient to do this. And so here's kind of how that augmented action looks. And basically, the intuitive explanation is that instead of using action A, we select an alternative action that has a slightly higher reward because we know the direction of positive reward with respect to action. And we add that as well to the experience buffer. And so this is, you can think of it as kind of like one step in gradient descent. It's kind of just like a linear step. And so we have this threshold parameter delta. And then delta is essentially just like the step size. And so you can imagine if you set like high enough delta that you could overshoot like a local maximum and produce some error. So yeah, we did some experiments on this, testing different hyperparameter values. And so here's kind of the reward curves for a single agent figure 8 traffic flow optimization task in Sumo. And the goal is to just increase traffic flow for the entire system. And we basically just benchmark different threshold hyperparameters. And you can see that like with a threshold of 0.2 and 0.4, it gives us the best results here. And if you lower the threshold too much, then you kind of reduce the gains of improving the sample efficiency. And then the baseline doesn't converge actually to the optimal solution. So here's a visualization of the learn policy. The AV is in red here. And so, yeah, you can see on the left here that the baseline policy did not actually converge. Actually, what a lot of policies that converge to unoptimal solutions do is they kind of slow down. And then, as you can see, you have all the vehicles just trailing behind the lead vehicle slowly. And this is what they find to be the best solution. But in like an optimized policy, it will keep like flow going through the figure 8. And yeah, that's basically what it would look like. And so we also benchmark this across different Carla test scenarios. So you saw the benchmark in the Sumo figure 8, but now we benchmark in Carla. And so Carla has 26 evaluation test scenarios, and we evaluate the mean traffic flow on the top and fuel consumption on the bottom across all 26. And you can see that like for a lot of scenarios, we actually improve the traffic flow quite a bit in the local lane. And there's some scenarios where you can see that the traffic flow is basically none, and that's basically failure cases of the baseline model, where if it doesn't move at all and it doesn't drive forward, then the traffic flow is completely bottlenecked. So yeah, and then an interesting observation is that as you increase traffic flow, you might expect that fuel consumption increases as well because you're driving more distance. So we actually had a fuel consumption reward term that tries to minimize it as you increase traffic flow, because an undesirable outcome for reward hacking the traffic flow is to just have this stop and go behavior. So like to accelerate greedily and then brake. And that would also raise the traffic flow on average, but we don't necessarily want that because that wastes fuel. So we also maintain about the same fuel consumption with this policy. And so here's a qualitative result on just following the lead vehicle here. And you can't see, but there are vehicles behind this current vehicle as well. And what happens on the top, if you can think of it intuitively, is that we're trying to learn actions jointly. So like steering and acceleration jointly in a policy. And the top is actually a work called Learning by Cheating. So it also has the same setup where there's a privileged agent distilling information to like a student agent here. So then, yeah, as you can see, our policy is able to get past this traffic light. And it's possible that there's a bias in the data set where like at most traffic lights, the vehicle stops. So this was interesting. And so some takeaways of this work is that our phase 1 model supervises phase 2 in a distillation-like fashion with respect to acceleration control. And the results in the paper reflect not only improved global objectives like traffic flow, but we also perform better on individual objectives, which is from the Carla simulator on completing route goals. Yeah, so this also complements existing work in autonomous driving. So this can be implemented as a wrapper on existing end-to-end driving work, especially those that compete on the Carla leaderboard for end-to-end driving. But there are some limitations to this work in that current traffic simulators are not parallelized and unoptimized. And so as I mentioned before, co-simulating Carla and Sumo can be very expensive. It doesn't necessarily give us the speed that we want for like 1 million simulations. So this is one drawback, even if we improve on the sample efficiency. And the other thing is that existing benchmarks in autonomous driving do not consider difficult traffic flow tasks. So as you can see in the Carla example, it the traffic may not have been as dense as we want to fully showcase the benefits of this work. So basically lack of benchmarks in terms of mixed autonomy. So now I'll talk about the next one, which is low-level traffic dynamics in autonomous driving. So this work is called Deep Stochastic Kinematic Models for Probabilistic Motion Forecasting in Traffic. This title is a mouthful. However, it's kind of a play off of a previous work that introduced the deterministic version of it. And so basically, what I want to preface with is that in this particular project, we focus on probabilistic trajectory modeling. And so the type of paradigm that we want to focus on is called one-shot regression models for trajectory modeling, and is basically what you might imagine the naive task would be, which is predict all future states at once for all time steps. So if you have future 80 time steps, you would predict all 80 at once. So this is given the past states and historical context. So we're basically just trying to predict the distribution of future states given the past states in context. And so there's two pros to doing this kind of prediction as opposed to autoregressive approaches and next token prediction, and that it's cheaper to learn and it works well in most cases. And this still achieves good benchmark results in like empirical observations. So if you were to benchmark this against autoregressive models, it looks pretty much the same in terms of evaluation. But one downside is that it enables anti-causal reasoning because you are kind of just predicting all at once. And there's not really a relationship between one state to the next. And so we kind of focus on this last point here. And the question is, how do we enforce causality and feasibility in some way? And the simple answer is we could start with modeling trajectories via the system that they were produced, aka vehicle kinematics. So the idea is super, super simple. And we basically just predict inputs to these kinematic models instead, like the bicycle model, and then we roll out the trajectory with time integration. And in this way, all time steps are directly related to the state at the last time step in some way with a gradient. And then the full trajectory that you end up unrolling is guaranteed to be kinematically feasible according to the model that you use to unroll it. And so the obvious question is, well, this seems like low-hanging fruit. Why has no one done this? This kind of seems like, if we're predicting trajectories, why not we just, incorporate this model in? So actually, state-of-the-art models are probabilistic, and the use of Gaussian mixtures as like a paradigm for predicting trajectories is kind of recent for a lot of like SOTA deep learning approaches for trajectory modeling. And so I want to say like this way of modeling trajectories has become more popular since like 2022. And as a result, basically there's this almost like this gap between previous work in using kinematic models for navigation and also current work that works best for trajectory modeling in deep learning settings. And so the challenge here is really just knowing how variance and uncertainty roll out with respect to the bicycle model, because the deterministic case is kind of easy. You just take the predicted actions and just unroll it like a simulator. But the question is on the uncertainty and the variance. And so the idea here is actually very easy to implement. So just step one is that a Gaussian mixture head produces a prediction of action distributions. So for direct examples, we can say steering and acceleration. And we basically just derive analytical linear approximations to the bicycle model to convert Gaussians of actions to Gaussians of trajectories. And then we use Euler integration for vectorized rollouts. And we did consider other integration methods like Runge-Kutta. These are more accurate, but they're more expensive to compute, and it's a little harder to do these like vectorized rollouts at once. So it will add essentially more compute to the actual training. And so the entire the entire analytical formula for like converting actions to trajectory is like basically here. So this is kind of like the core contribution here, which as you can see, it's very algebraic, it's very simple. And the implementation is also very easy. You kind of just like add this into your prediction head for trajectory prediction. And that's basically what we're proposing here. And in the paper, we look at 4 different formulations for this kind of transformation. And so we don't just look at acceleration and steering, we also look at like, what if we do different components, and what if we look at speed and heading, which is like the first order. But the main idea is that the computation is simple and differentiable and basically adds like next to nothing for current models. And so we run experiments using Motion Transformer, which is a state-of-the-art one-shot model for motion prediction. And then we train on different settings with the Waymo Open Motion dataset. And so on the tables here, you have training on like full-scale training on 100% of the dataset, which is huge, by the way. The dataset is like 1 terabyte of trajectories. And then you also have 1% of the we use 1% of the data below. So this is kind of like in the case that you have not as large of a data set to scale on. And we do get like very consistent like metric improvements across forecasting metrics here. But most notably, we get the biggest gains as expected when you train on just 1% of the data set in the unoptimal case. And yeah, so there's some observations here. As you can see for the full-scale training, that formulation 3 works best. And that's steering and heading. And this is somewhat explainable by the fact that we use linear approximations when we try to do these conversions. So those approximations come with error bounds. And so as you continue to approximate to the second order, those errors might also increase. So it's possible that the acceleration and steering, it works slightly worse than steering and heading, or heading and speed, due to like the increased error from approximations. And so some takeaways from this work is that formulation 3 provides the most benefit in performance for large scale learning. Formulation 2 provides most benefit in performance with smaller data sets. However, formulation 4, which is acceleration and steering, as expected, is most robust to small perturbations at test time. And it's also fastest to converge during training. And so you can see the full work for the other experiments. But basically, this is just showing, for example, when we train on 1% of the Waymo data set, you can see that the baseline hasn't quite converged yet. And so this is exactly a case why we're motivated to do this work, is because at points, the model may predict like these like physically infeasible trajectories that cannot even be performed by a vehicle in the first place. And so the idea was essentially like, why not would just avoid it entirely by directly incorporating this kinematic model. And so, yeah, so now I'm going to move on to part 2 of the thesis, which is studying human factors. And we kind of do this in 2 parts, with one with a user study and one with like modeling a latent variable. And so just to compare these 2 approaches, so for user studies, the challenge is basically to give to design a user study. And we need to make sure that this user study is actually measuring what we want it to. So the biggest challenge is the design. And then for the latent variable approach to modeling driving style or human factors, that latent variables are not easy to interpret, and it's also hard to control for. We don't really know what like it's modeling it within the data that it's training on. And it could easily represent like this spurious correlation within the data set. And so in this next session, we'll talk about user studies, and the question is, why virtual reality user studies? So the main goal here is to investigate the mapping between driving style and trajectories. And driving style, as mentioned in the thesis statement, we believe it's most useful as a variable to model in edge cases. So how do we get driving style to edge case trajectory pairings? This pairing is not feasible in the real world due to safety concerns, costliness, obvious things. And so we want to investigate this with immersive virtual reality simulations to start and find leads on it. So this was a preliminary work that I did a few years back. It started as a course project actually, but actually led to some great outcomes. And what we did was we had Carla, right? And then some researchers at CMU developed this virtual reality wrapper for user studies. And so we had this virtual reality simulator that to start with to run simulations and user studies on. But the question is that like Carla was actually built for autonomous driving policies as a test bed. It wasn't really built for user studies or user experience or running in real time on a virtual reality headset. So we had to do like almost this human feedback loop of trying to tune the simulation parameters so that we could make it optimal for the human experience. And so we ran this pilot stage and we found like this optimal set of parameters. And then we also, once we set the simulator parameters to the best possible we could off of the pilot stage, we then did a data collection stage where we actually scaled up the number of people. We basically just collected, this was the portion where we collected paired data here. And so in this user study, this preliminary user study, we collected data of 24 participants, and you can see the demographics on the right. And most of the recruiting was done physically or through flyers or word of mouth within the computer science department here. And the first stage that a user will go through in this study is a questionnaire, which includes the usual briefings, consent forms. And we also put the users through a baseline simulator sickness questionnaire. So like, how well are you feeling currently? Let's benchmark how you feel before we put you through the scenarios. And then the other thing that we had them do is take this driving style questionnaire called the multidimensional driving style inventory. And this was created back in 2000 by traffic psychology scientists. And so it's kind of been used as a benchmark to measure someone's driving style through a series of questions. And so we had them take this questionnaire to kind of give them coefficients for 8 different driving style factors, which includes like anxious driving, reckless driving, angry driving, things like that. And then the second stage, that's when they actually put the virtual reality headset on, and then they experience a permutation of 4 scenarios to start. So these scenarios, as you can see, it looks a lot like Carla if you've used Carla before, but basically what we used was this virtual reality user study wrapper. And so here is basically what it looked like. So our setup, we use this Logitech gaming wheel and use basically whatever we could find in the immersive media lab to put this together first. And you can see some scenario roots as well here. So the user trajectories from the 24 participants, we plot it on the bottom, and you can see how they react to the pedestrian crossing. The red?
Yeah.
Oh, this spinning, it's supposed to be for gaze tracking, but it wasn't working in the simulator, so I would ignore it. It's just doing default spinning behavior, but it's supposed to be gaze tracking. Yeah, where they're looking. Yeah, so that'll be important because that's a limitation of this work. So we look at does the assess MDSI styles, which is the driving style inventory that I mentioned before, does it correlate with actual driven trajectories? So we test correlation between scores for each MDSI factor. So you can see it on the rows here, and trajectory properties that you can directly measure from like the trajectory points. And we basically just look at things like cumulative changes in steering, throttle, and braking, and different metrics of like the trajectory curves. And so, yeah, so the results, we didn't quite get something statistically significant for each driving style, but we did get some interesting curvature correlations for angry driving, and also control input correlations for patient and careful driving, which is interesting because yeah, we might find that a lot of these categories are not like mutually exclusive. We can see that they probably correlate with each other to some degree. And so the other thing that we had a question about was, so in the last correlation table, we looked at linear relationships. So what if the relationships are a little more complex than linear relationships with driving style? So we just do a very simple experiment where we take like a 2-layer multi-layer perceptron, and we just try to model like almost overfit the data for a particular scenario to predict the driving style coefficients. And the idea is like, is there a function that can kind of like map the trajectory to some sort of driving style classification? And so if on the right, you see like the control, and in the control, each point represents like a gradient of greater magnitude for that particular trajectory point. And we see kind of like what we expect for like an overfit model. So this model kind of like, it got to a sufficient accuracy, it overfit. And you can see that it's somewhat memorized the mapping between driving style and the actual trajectory because of the uniform points. But what we saw was interesting was in scenario 1 with the jaywalking pedestrian, there was a very obvious like almost like concentration on specific parts of the curve prior to interaction with the pedestrian. And it was very interesting to see that like we didn't get this same like uniform overfitting on the pedestrian case. So that was an interesting finding as well. And the question is, how effective is VR as a medium for driving studies? So all participants are regular drivers and own a driver's license. This was part of our screening. And 79% of participants recorded high levels of immersion. So VR did work to some degree to immerse the participants, and 7% of participants experienced severe simulator sickness, which is bad. Some qualitative observations that we had was that some participants actually instinctively grasped for controls that didn't physically exist. And this was interesting because everyone walks into the room and they see the setup and they see there's nothing around them, and they're sitting in like this office chair. So the fact that they're grabbing and they're doing this like almost instinctual movement is kind of a good sign that, they might be immersed to some degree. And we placed some bumps in the scenarios. Like if you remember scenario 2, there was an obstacle on the road, but it's kind of hard to see. So actually for that one, only one participant noticed such bumps. And so this is the limitation of the simulator. And also most participants did not use the built-in mirrors, which seems concerning, but the mirrors actually, it takes a lot to render them in the actual simulator. And so if we turn off mirror rendering, it actually bumps the frames per second. But we had to sacrifice some performance to actually render the mirrors. So it was surprising that people didn't use the mirrors. I hope, or I would think that people use mirrors in the real world. So this was kind of like a negative sign. So we wanted to improve this work. This was like the kind of like the first study we found, like we figuring out the nuts and bolts of virtual reality user studies. And a lot of limitations for this study stem from hardware and software. And so one was that frame rate was reduced to run simulation in real time. So like, as I mentioned before, Carla is for benchmarking autonomous driving policies. It's not for user studies on a virtual reality headset. So this adversely affects realism and sickness. And the number of scenarios were limited to what was implemented within ScenarioNet and Carla without major engineering modifications. So those 4 scenarios that we saw were kind of built into Carla, and they're used for testing autonomous driving policies. They're not used for testing humans, and humans can much easily tell what's realistic and what's not. And also traffic sim behavior was not realistic in the baseline simulator. So the vehicles also drove extremely slowly and didn't react the way that you would want them to if you interacted with them. And so this is kind of a improved simulator that was published at IROS 2024 last year. And we essentially just decided to make one from scratch. So we were thinking, okay, let me mute this. There is sound. So we thought, let's make one from scratch with all the functionalities that we would like. That's actually built for user studies. And so this was a huge engineering project, and I'd like to thank the engineering team that also helped with this from MRC. And basically, because we had full control over the design, we expanded the simulator to model 8 National Highway Transportation Safety Administration pre-crash scenarios, and then some more self-defined scenarios that they didn't include, like deer crossings. Because we also created this ourselves, we increased the frame rate by getting rid of functionalities that we didn't necessarily need, and that we can collect post-hoc. Like, for example, we don't need to be collecting LiDAR sensor data in the moment. We could first collect the replay, then attach the LiDAR sensors later. And then we also have more human-evaluated realism in traffic dynamics. So in this updated user study, we wanted to benchmark how much of an improvement we had over the previous baseline simulator we used in the first one. And we do get improvements all around in these different categories. So this was a big improvement off of the previous one, and also just off of frame rate and user experience. I think there is a clear difference between our updated simulator and the baseline. And so another nice like segue from the simulator is that we then reran the user study in even larger scale. So this was a data set that we adapted for trajectory forecasting tasks, and we've kind of released in the same format as other popular data sets. And this was published at ICRA 2025 this year. And so we basically used the same user study design as the preliminary study, but instead we conducted it within the new simulator Traverse instead of the baseline simulator. And so we might imagine that the actual behavior that we're measuring in the simulator is more realistic than what we had originally. So let me see if I can show some. Yeah, so that's like the merge scenario that we mentioned in the motivation. And also this is similar to the first work. This is co-simulated with Sumo. So all the vehicles here are controlled by Sumo as well. And so if you do drive in front of a vehicle in this case, it does react accordingly and brake. So I'm sure everyone has kind of seen this at some point on the road. And I don't remember where in the video it showed, but there was an example of cutting in front of a vehicle and showing that it was reactive. I'm not sure where that is. Maybe it's in the beginning. But yeah, some takeaways of this work. So there's three parts to this. So in the preliminary study, we designed and implemented a user study for collecting paired driving style annotations and pre-crash scenario trajectories. So a lot of the work went into actually designing the user study for this. And then we noticed a bunch of limitations, and we collaborated on creating a new in-house virtual reality simulator for user studies in driving. So we wanted to improve on all the points that we had missing in the first study. And then finally, we wanted to make use of this simulator and provide a data set and run the user study ourselves and provide a data set for the community to use. So this now I'll talk about the second part in human factors modeling, and this is with kind of like the big data latent variable modeling approach. So no more user studies here. And so this is a more recent work that's currently under review. But essentially what we're trying to do is we're trying to extract driving style representations in a parameter efficient way and have it modular so that we can kind of influence the style of the outcome trajectories. So to motivate this, here's a very simple example. So what variables influence a driver's trajectory? So prediction is often conditioned on several variables. So first we have intent, which is where do we want to go? So you can think of this as like what our goal is. Do we want to be in this lane or that lane? And we also have context. So like what is around us, what's the road, what's the vehicles, and the context can influence how we achieve our intent, how we get to our intent. As you can see here, there's two different green lines here. And in both cases, we get to the right goal post, but we have the same context and the same, set of goals. But we have two different outcomes. And so when you measure this with like distance metrics for trajectory forecasting, this discrepancy matters a lot in terms of meters, especially if you do by time step. And so what describes this discrepancy? We have that intent and context are the same. And in this work, we hypothesize that this variation, when you kind of like account for intent and context, this variation is described by driving style. So that's kind of how we set up the modeling problem. And so the goal here is that we want to model driving style with interpretability and controllability, which is much harder said than done. And ideally, we want to choose outcomes in the same scenario under different styles. So we want to have like this, let's say you encounter this rare event in the real world and you have this real world event. Ideally, we would love to be able to just tack on this like modular, this module to influence, what if this driver was an angry driver instead and see the same outcome without having to collect, that edge case again in the real world, kind of like a needle in the haystack. So we also want efficiency without losing base model performance. So you want it to be kind of like easy to train and modular so that it doesn't add too much because modeling driving style is almost like a secondary thing to having good performance. So we definitely don't want to lose the base model performance. And then we also, like I mentioned before, we want novel scenario generation from real world edge case replays. So we want to make the most out of the data that we actually do collect that's rare. So here's our proposed approach. And so this is kind of a lot in the diagram, but we'll break it down step by step. So first, what we do is we create like these social forces features, which is we handcraft these repulsion force features between vehicles. And then we fuse these with like a single dense layer with context features from the encoder. So by the way, this entire thing is built on top of an existing encoder-decoder trajectory prediction model. So the green boxes can be kind of generic and you can replace it with like pretty much any encoder-decoder type trajectory predictor. And so we construct these social forces features, which I mentioned how we compute the repulsion forces on the right side. And then we feed this into a latent variable router. And we call it a router because it eventually gives us like the weights that we use to mix experts later. But in the case of this setup, you can think of it as like a bottleneck. It essentially produces like a categorical distribution or logits. And then we sample from those and then use a social forces feature reconstructor to reconstruct the original features that we fed into the to the router to begin with. And then we just do a very simple like L2 objective on reconstructing these features. And so this really looks like, if you've worked with variational autoencoders, this looks a lot like that. So we do a very classic like VAE setup within what we're doing here to kind of look for latent variables that we hypothesize can be extracted from social forces. And so this is one objective that's going on. And then the other one is that once we have like these logits that are representative of the latent variable that we're trying to model, we want whatever sample that we classify into that latent class to be optimizing like the right expert. And so we have this collection of low rank adapter experts, which are really just these low ranking matrices that are used to make updates to linear layers within the decoder. So they're kind of just they're very parameter efficient and yeah, they basically an alternative to find like full scale fine tuning. And then here we just have a mixture of LoRa experts. So if we trying to model if we, for example, want to model 3 different driving styles, we would model 3 different LoRa experts. And then the routing logics here would provide the weights for like how much we activate each expert during the forward pass. And so, yeah, that's basically how the entire structure works. So we have this VAE kind of objective going on the top left, and then whatever the latent variable being predicted by that process is, we use it to then weight the expert and try to like encode the latent representation into different modules that are kind of like fine tuning on those particular samples. And so for inference, we basically just use a weight of 1 for the corresponding LoRa. So like, let's say we have 3 different driving styles modeled. If we want to do inference with a particular driving style, you just kind of zero the weights of the other LoRa modules and just keep the one of them as 1. And then we again implemented this on Motion Transformer. It's open source, it's state of the art, and it's recent. But that is a one-shot probabilistic regressor. So we also implement it on another paradigm, SMART, which came out last year. And SMART kind of models trajectories like language models do, and they tokenize, discretize the problem, and treat it as next token prediction. And the loss is simple. We have the original trajectory prediction objective, which is just like the Gaussian mixture model loss, or the token loss from the SMART objective. And then we also have VIE objectives on the social forces features. So in our results, there's not that many works that kind of do this, so it's hard to find like a one-to-one comparison. But what a lot of works have done is mixture of experts and also similar paradigms in multitask learning literature. So that's kind of what we test, but these can be kind of interchanged within our method. It's not our method is not limited to just one mixing scheme. So we look at different ones here, and not all methods allow for differentiable, like for gradients to be propagated to the router. A lot of them kind of just have like a, on and off switch for choosing experts. And so that kind of cuts off gradients to the router. So a lot of them are almost like have limitations in terms of like the differentiability. But here's some results on Argoverse 2, which is a trajectory forecasting benchmark, and we test different weight mixing schemes. One thing to note is that MOV on the bottom is not used with LoRa's as a fine-tuning kind of approach. They use like a much simpler vector update, scaling vector update to the weights. And this is also even lower of a more efficient fine-tuning paradigm, which is really interesting because we do get like the best results on general performance with MOV. And so we also want to look at performance across different trajectory difficulties and different driving styles. So we have common difficulty, and just like very intuitively common difficulties where if you were to just like predict a trajectory with a common filter, how much the actual ground truth deviates from that like kind of naive prediction. And so we can see here that CAT, which is one of the mixing schemes that we've used, actually improves the most on hard samples, which is interesting. And overall, we improve on performance slightly without any additional data. So basically, this just checks the box of that we maintain competitive performance in trajectory metrics. But the question we want to ask is this enough? Are traditional trajectory prediction metrics sufficient to quantify driving style? So like a lot of the metrics you saw were distance-based. And so you have things like minimum displacement errors from ground truth. And the question is, does this really capture driving style? Which is what we're trying to model. And so in this work, we also propose a metric called style miss rate. And the idea is we want to keep this as simple as possible. We don't want to make this metric super convoluted and hard to interpret. And so the idea here is that we just want to measure the ratio of samples where none of the predicted modes, so for like a Gaussian mixture, you might predict 6 different trajectories. This is where none of the 6 share the same driving style as the ground truth. And we define driving style differently from how we do in the model, so that there's not like any like confounding between how we model it and how we're measuring it. So we basically just do something very simple, and we train a Gaussian mixture model with 2 modes. And we do this off of basic second order kinematic properties like acceleration, like angular acceleration, things like that, jerk. And we just use 2 classes. We don't want to complicate it. Just make 2 classes, and if none of them belong to the same 2 classes, then it's a miss. So this was pretty surprising, actually. So when we do this, we do get a very obvious difference between the baseline and versus when we apply our method. And so here, the lower is better. Yeah, so this was kind of interesting, is that if we do come up with a metric that kind of almost measures like second order kinematic consistency between ground truth and the predicted trajectories, it was quite surprising to find that, like at perhaps our method does predict something more consistent with the ground truth. And so the next thing we want to look at is, do the latents mean anything? Is it even related to driving style? So we do basically what the style miss rate also computes, and we want something more intuitive. So we basically plot the absolute kinematic properties relative to expert 2. So each of these are on different scales. So we want to make it like more readable. So we use expert 2 as like the baseline anchor for like to sit at 1 in each of these bars. And you can see that for the longitudinal movement, which is like acceleration and jerk, this would be like along the lane. We don't really see much difference between the experts when we actually do the training with our framework. But we do see most of the difference coming from lateral movements. So this is like, that has to do with steering. So this is angular acceleration and angular jerk. And so this was kind of interesting. And essentially what the takeaway would be that the experts, what they're separating on in lane space has more to do with like lateral movements rather than longitudinal. And another thing that we wanted to confirm was whether the router learns meaningful latent classification. So how do we know the router isn't just like collapsing and learning redundant representations for each expert? So we just plot like the TSNE visualization of the router embeddings to make sure that like, and we use like, we color code by the argmax of the logits. So it's basically just to see whether or not there's some meaningful clustering. And what we don't want to see is like one giant blob with all 3 colors, basically. Yeah, so then another interesting result that we had was to look at whether 3 was the best number of latents to model. So the choice of 3 for latent classes is supported by 2 pieces. So one is we did like an experiment doing hyperparameter sweeps, which vary the number of latent classes modeled. So you can see on we try different hyperparameters for the number of classes or number of experts modeled. And you can see that for the most part, it's very consistent. What's interesting is as you increase the number of experts, the hard performance actually goes down. But right at 3, we have this outlier of like 2.49. And so that was kind of interesting that like perhaps setting a number of 3 classes provides more meaningful separation for hard cases. The other piece of evidence that we have is an NHTSA study on risky behavior. So this involves actual traffic researchers, and they do a 100-car user study where they follow 100 drivers over a longer period of time. And actually, at first, they wanted to separate drivers into 2 groups. But what they found was that, like empirically, from their experience, there's more separability when there's 3 groups of drivers, according to risk. So that was like another piece of evidence. And then here's some like qualitative results when we actually like, plug in different experts. Yeah, as you can see, if you recall from the kinematics plot a couple of slides ago, the most difference in behavior actually results from this last expert here with the smallest probability. And so it was kind of interesting. What I suspect is going on here is that there's a yellow light. And so each vehicle has different reactions to this approaching this intersection. You can see like this middle style kind of like brakes more harshly as it approaches. The first style brakes, but is less harsh about it. And then this third style kind of just like tailgates this vehicle right in front and doesn't really brake at all. And so that was kind of interesting behavior that we wanted to see. And also just keeping in mind that the way we modeled it is that we also keep the intents constant for each vehicle. So that may also involve staying in the same lane. They may not necessarily change lane if the intents are constant. And here was like a very interesting edge case that we found. So this is, I don't know if you can see, but there's this tiny dot on the side of the road on the right. And that's a pedestrian that's almost like trying to cross the road. And each style has like a different reaction to this pedestrian. The first 2 styles, as you can see, like from the original plot, we may not see as much difference between how they react. But on the last one, which is like like from the prior, the least common reaction would be to like kind of like swerve right. And so that was kind of like an interesting emergent behavior that we found from this latent variable modeling. And that was just like a very interesting like qualitative example that we observed. And so some takeaways here is that parameter efficient mixture of LoRa frameworks. We proposed this framework to modularize latent modeling of driving styles for trajectory prediction. And we also designed this router that's based off of handcrafted social forces, and we fused them with context features. And we also propose a style miss rate metric that captures inconsistency between ground truth driving style and predicted driving style with a different paradigm that's more simple and off of binary classification. And then we also do some qualitative analysis on extracted latents, which I think some of the analysis that we've done was not previously explored in other works. So that was pretty cool. So this is the last work that I'll talk about in my thesis, and that is for modeling sensitivity for natural corruptions. So this is a little bit of a different vein from the other works that I've talked about, which worked in the trajectory space. This is more to do with sensitivity in for perception. So basically, this work was presented very recently at ICML 2025. And this was a collaboration with the Army Research Lab. So the motivation here is that we want to address natural corruptions. And these are a type of noise that occur, as you might guess, naturally. So this is as opposed to things like adversarial attacks, which are produced synthetically by some actor. This is natural things that basically would be described by edge cases or just unpredicted noises. So this includes rainy weather, motion blur from data collection process. If you crowdsource it, you can't expect, optimal data to be crowdsourced. Or things like JPEG compression from dataset processing. Some of these things you can't really account for. But nevertheless, like the data could be used as part of your training framework. And in recent work, what was found was for segmentation models in particular, the greatest robustness boosts were more from architecture design. So things like segformer were introduced for robustness. And then also the existence of foundation models now and just these like robust weights that you can just kind of fine tune downstream for different tasks. And so this is kind of like what the current trend is for like upping the robustness on any particular perception model. But these are still susceptible to performance degradation when fine-tuned, especially if the target data set you're trying to deploy with is a smaller data set with limited number of samples. And so we want to take a look at sensitivity analysis here, which essentially is just the sensitivity of the neural network performance. So this is like accuracy with respect to perturbations in the input data, which we can think of as augmentations. And so in other words, we basically want to measure what is the change in accuracy when we kind of like add changes in noise. And so the key idea here for what we think could boost robustness from like the data side is to basically just sample uniformly difficult noises to strengthen the model. So the approach here is basically just spending wisely. So previous work has shown that augmenting training with sensitivity analysis does work, but this is very expensive because they do so with Monte Carlo sampling. And sensitivity is a function of model accuracy. Many forward passes are required to evaluate this curve of like to look at like how sensitive a model is, because we need to run inference pass to figure out what the model accuracy is. But one observation we make is that in general, we know that neural networks trained on generic data will produce a monotonically decreasing accuracy as we increase noise on the data. So we kind of have a general picture of what the accuracy versus noise curve looks like. And we basically come up with this function G, which the input is alpha, which is a perturbation intensity constant. And this basically is just a function of mean accuracy of any given model. And then with the kernel inception distance as a way to kind of like standardize and quantify how different the clean data set is from the augmented data set. And then this basically like what we can do is we can like come up with this function as the vertical axis, which is kind of like, you can think of the vertical axis as a function of accuracy. And then we also have on the horizontal axis, like a function of augmentation intensity. And so when you actually like figure out what values of G are along for different values of alpha, we can then sample uniformly alphas that produce uniformly distanced G's along the vertical axis. And this is basically what happens is like if we have a bounded alpha, we basically can just figure out what are the areas that we actually care about. So knowing that we actually want like uniformly difficult alphas, we can actually just find out iteratively like what alphas are actually producing like these G's along uniform on the vertical axis. And so we do this until it converges, which is basically like as you repeat this process. And this could seem like it could take a lot of iterations, but in practice, when we actually tested it, it really just takes 2 iterations max. So this is quite efficient when you actually run it in practice. And basically what we do is like with these alphas, we construct a categorical distribution to sample from, and then we kind of put more weights on like the alphas where we have lower model accuracies. So this is typically going to be on alphas with like higher intensity values, and we kind of just put more weight on them. And the intuitive ideas here, you can think of it as like, for example, a teacher giving a practice exam. The teacher wants to know what problems the student fails on to give like a sufficiently, accurate practice exam with easy questions and hard questions to challenge the student and also make sure they get the most out of the exam. And so we compute these noise parameters for a bunch of different augmentations, and these are all very simple to compute. They're nothing crazy like, a lot of people are doing like generative augmentations and stuff like that. This is just very simple augmentations that modify color channels and do geometric transformations. And so these are some examples of photometric transformations, and then we also have geometric transformations that involve like rotation, basically just affine transformations on the image in both directions, positive and negative. And the results are pretty good compared to other data augmentation methods. So here we basically train on cityscapes data. We train on clean or sunny, clear weather cityscapes data. And here this is like evaluation on adverse weather. So basically the models that are trained here have never seen adverse weather yet in their training distribution, but are exposed at test time. And you can see that the performance is actually much better across most scenarios with ours. And so here's some like qualitative results on rainy data. And something with rainy data is that it does produce like different sky coloration values and different kind of like textures on the roads. And you can see here that like between like other augmentation approaches, we do get a lot more artifacts when you test on rainy weather. But ours does produce less artifacts, and in particular can segment the bus much better than other approaches here. And we also test not just on driving. So even though driving was the main motivator for this work, we also look at other domains like medical segmentation. So you can see here, this is like organ segmentation. And yeah, we do get better results when you introduce noises like JPEG compression. So this is where you just like continuously compress the image and it produces some sort of like noise from like the repeated compression. And then this is synthetically induced motion blur. So when you kind of apply motion blur to the images, how well does the performance hold up? And trivial aug, which is probably I think one of the most recent augmentation approaches, does not handle this particular perturbation well, which was also interesting. And so some takeaways of this last work is that we propose an efficient adaptive sensitivity analysis method for online model evaluation. And this speed up is due to utilizing approximate monotonicity of model sensitivity. And then we also propose a data augmentation scheme that leverages the sensitivity analysis. So you can not only just plot the sensitivity analysis to see what the model's sensitive to, like how the curve looks for analysis, but you can also use it as a data augmentation reference. And then we also do evaluation and analysis to show that this does work across many different domains. We also do like aerial data. We do driving data, unmanned ground vehicles and things like that. We show that it works across all different kinds of domains. Yeah, so that kind of brings me to the end of the thesis. So this is kind of like at the we've kind of like reached the end here. And just as a summary, here's kind of just like an overview of everything that's been covered. So we looked at differentiable traffic sim models with end-to-end driving frameworks, derived and applied approximations for time integration of the kinematic bicycle model for probabilistic trajectory forecasting. We looked at user studies for human factors, and then in the wrong order, driving style learning through latent variable modeling, and then finally fast estimation of model sensitivity. And so there's quite a few future directions here, and it's pretty exciting. So there's still some work that I would love to see that kind of like continue this. And one is traffic flow models have yet to be implemented with deep learning based simulation models. So I used traffic flow models to learn like an optimal acceleration agent directly. But it would be nice to see like a generic traffic flow model be almost used as like the skeleton for more robust traffic systems. And it's different from physics sim in that like physics sim can be used to get the exact positions. Traffic flow is a little more fuzzy on that, but I do think that the gradients would be very useful for trajectory forecasting. Also, driving style isn't fully interpretable yet, so we did a bunch of analysis, but it's not quite like there in terms of is it something that we can like kind of observe and quantify directly? And also, we lack benchmarks for driving style. So this requires paired real-world data, and we've kind of attempted this with user studies for virtual data, but we kind of have this unmanned territory of like, what is the sim to real gap in the trajectory space between virtual and real data? So there's that, and it would be nice to have paired real-world data to measure this. And also, I did kind of two sides of the user studies. So one is like from user for the human factors. So one is with the user studies and one is with latent variable modeling. It would be nice to have a work that kind of bridges the gap and uses insights from one and the other. And then right now, sensitivity analysis work is only applying to images for like perception tasks. So the question is like, if we can do this something similar with trajectories, it would be super, super interesting to see if there's natural behaviors that kind of just like break behavior models. And I think this would be really interesting as an analysis to see, you know, like this would help us define what exact behaviors would be edge cases in terms of decision making. So here's just a list of publications, and the highlighted ones are the ones that were featured in this presentation. But like all of these are works that I was involved in during PhD. And yeah, some acknowledgement finally. So obviously it takes a village, and this is like not like an all-inclusive list. I couldn't even put names because it would end up being like 5 slides. But I would just like to thank, first of all, my advisor, Professor Lin, for advising me like for so long. I basically emailed her initially for a research opportunity when I was a baby researcher. And it's like looking back, it's been insane how much growth I've had and how much I've learned under her. And I also want to thank committee members for being here. You know, thank you for giving me 2 hours on your Tuesday. And also Professor Tianyi Zhou, who was a co-PI on a lot of works here. I felt as though he deserved also a shout out for being involved in a lot of the work that I've done. And also thank you to collaborators, Gamma Foodies, mentees, research mentors that I have, internship mentors, and grad school friends. And more on the personal side, I want to thank my family. Not a lot of people get to do a PhD 40 minutes from home. And so I feel like I had quite the special PhD experience. And, you know, like a very recent example is me moving out of my apartment 2 days ago. And like not a lot of people have the privilege of being able to just move out and go home to their parents before the defense. So that was like absolutely, I do not take it for granted. I go home all the time for food. I also want to thank my partner, Brendan, and his family for supporting me. And also, as you know, like I'm very involved with esports and gaming, and I have tons of friends who are also supporting this defense remotely. And those are very special friendships that I've had. Also, I have this gaming research reading group, GERG. Shout out to GERG. We do basically a reading group for that goes over like multi-agent game research and just human factors game research. And a lot of that helped with ideation for driving for me because the problem space is very similar and also built special bonds there. Also friends from undergrad. I went here for undergrad, keep in touch with a lot of friends. And also shout out to the CS grad office, especially Tom, Migo, Sharon, and Janet. Couldn't have done this without them. And the UMIAC support help desk. I don't know what I would do without my 6 terabytes of storage space on Nexus. And also Eastern Gourmet for being open until 11 p.m. most days. And also One Piece for being started in the year that I was born and still ongoing till now. So it's really been keeping me going every Sunday. So yeah, with that being said, thank you to everyone for tuning in, and I would like to open the floor to questions.
Okay, we are now gonna take questions. We'll start from the audience here. Very quiet, very shy audience. Go ahead.
I don't really understand what you said, but can you explain why you said you were able to improve the frame rate and you didn't have to have the LiDAR again?
Oh yeah. So basically, let me go back to show you. So just to repeat the question for online audiences, clarification on how we improve the frame rate in our updated user study simulator, as opposed to the original baseline that we used, which was a VR wrapper on top of Carla. And my answer to that is that Carla was originally built as a simulator to test autonomous driving policies. So the kind of like end user of this simulator is actually just like basically a neural network. And the neural network doesn't need the simulator to run in real time. So it could run super slowly. It would just be like the same in simulation time. However, so basically what this does is that you don't have this constraint for like real time experience. And so they've added all these like kind of heavy processing features. So for example, they attach all these fancy simulated sensors to the vehicle, like LiDAR sensors. And they have, for example, really complicated traffic modeling. And also they put a lot into like there's not as many optimizations basically because there's no need. So within graphics, there's like also the concept of culling, and they don't really do any culling. They just render the entire big city without like needing to worry about speed. So there's things like these that we don't really want in a user study simulator. And so we've kind of addressed them with our personal one that's more fitted towards user studies. Yeah, is anyone online? Do you have questions?
Yeah, hey, Anike, Dinesh? Do you have any question?
So are we starting the committee questions or we're still in the audience question?
How about anyone online audience?
Okay. So Laura, you did a lot of work and you
Yeah.
started with the differential simulator and you talk also about the simulator you're doing in the, on the gaming platform, the lab.
Mm-hmm.
So one question still comes up is, the holy grail in all this problem is still the sim to real gap, right?
Yes.
You started your talk about driving on Maryland campus, right? I don't know when you have college campuses are the most notorious for autonomous driving, I'll tell you. Even Google Maps don't work and
Yeah.
students work crazily. So while you do a lot of work on differential simulation and even the driver behavior you're doing in the lab,
Mm-hmm.
how much of sim to real gap is still there? And then you yourself, you say you live 40 minutes from work, so I'm sure you drive to Maryland campus on Maryland streets and campus.
Mm-hmm.
Where do you think are the biggest sim to real gap still, and what can we do to overcome that? Because real world human driver is, I think, one of the most unpredictable. There's so many cultural, location, timing, geographic factors. How do we deal with that?
Yeah, so I guess maybe to paraphrase the question is like how, like with all this work being done, like how can we make sure it's still practical with the problem of sim to real? So if we accomplish something in simulation, how do we still know that it's like it's useful for the real world deployment? And I guess my answer to that is to highlight two different paradigms for autonomous driving. One paradigm in the first work that I introduced was end-to-end driving, and this is kind of where we learn how to control a vehicle jointly with sensor data. So like, the input is the RGB, LiDAR, kind of like the multimodal inputs, and then you kind of just spit out this control, and that would be end-to-end driving. It's all in like one model. The more popular approach, because it's more interpretable, is modular for autonomous driving. This is where you have a dedicated perception module, a dedicated planning module, trajectory prediction module, and control module. And so these are kind of like just in separate modules that you can optimize separately instead of jointly. And so I would say personally, I believe the sim to real gap, the most challenging one is the visual portion, which is the perception. Because what we have currently is that we have like these simulators that can somewhat look almost realistic. Like we have things like we're all waiting on GTA 6. It looks super realistic. And we're getting closer, we're slowly closing the gap. But like I mentioned, what we don't know is the sim to real gap between like behavior, like modeled behavior in simulation versus real world. And I think that's kind of like one of the bigger future challenges of the work. But right now, I would say for current systems, like the biggest sim to real gap is in perception. And so if we can address like the perception gap, then for modular systems, the bird's eye traffic state that you saw, like with all the positions and the road network and stuff like that, that is very much a there's much less of a domain gap between real world and virtual there. It's more of like a distribution, like does the distribution of road lines match up with the distribution in the real world versus simulation. But those are a lot easier to address than, for example, like visual differences between pixels and images. That's much more high dimensional. I would say if the domain gap between sim to real can be kind of like allocated to the traffic state space, then it would be a lot easier. Basically, the short answer is that I think a lot of it isn't the perception part of driving. And so that might have more to do with like generalization. We can probably use like foundation models to help fine tune that and bridge that gap. But as long as we can all get both of them into that traffic state representation, we can kind of take that as like a domain agnostic representation of behavior. And I think the sim to real problem will be much easier in that case. Does that help with the question?
Yeah, so I see your point. I'm still trying to figure out if you have to work on this for now, I know you're going to Waymo for the next 5 years, what would you do? Let's say example. So the company with the most data right now is Tesla.
Mm-hmm.
And they have 7 million cars, including mine. So I give them free data. And there's a whole debate on camera versus LiDAR. Let's not get into that. That's a sensor problem, but camera.
Yeah.
Here's a company which has 7 million users, whatever,
Mm-hmm.
I don't know how many using at active time, collecting, they're probably the biggest collection of real world traffic data.
Right.
And I heard they also move into end-to-end. That's again off the record, no confirmation, because that's why they're doing it. So if we get that level of data, and they're not only just US, they're worldwide. They went to China, they went to India, so think of very diverse data. Is
Mm-hmm.
that the way to go? Is that the best possible option we have, or what would you do differently?
Yeah, so I don't necessarily think so. I think for just adapting to any city, fine-tuning to a city, collecting more data makes sense. I think like at some point you still have to do some level of fine-tuning to adapt to a particular city because every city has different driving behavior and different kinds of like landmarks and features and different traffic signs. But I don't think just scaling data is quite the solution, especially as I mentioned, like you have different kinds of edge cases with behavior. And so I think collecting like a specialized data set would help with that in analyzing the behavior, but I think that there has to be some special modeling techniques to look at specific things like traffic dynamics and driving style within those areas. And I also think that there's also simulation modules. So for example, you asked me like what I'll be working on after grad school. So I'll actually be working on simulation. And basically like a big question in simulation is like, how do you simulate the cases that you don't have data for? Because the whole purpose, it's like a chicken and egg. You want to simulate the things that you don't have data for, but a lot of the simulation frameworks require data to simulate them accurately, especially if you're relying on deep learning. So a lot of like what I want to work on in the next few years is essentially just yes, we can use data to help generalize the model, but we can't purely rely on data because the purpose of the simulator is to also simulate edge cases. So we have to kind of apply some modeling approaches for that. So I hope that kind of answers the question there. Yeah, does that help?
Yeah. I hope please do it soon and do it for the edge cases in DC so I can drive autonomously. Hope you can solve the problem for I'm getting old, so I need your help to commute.
Yes. I hope so too. I would like to not drive.
Thank you. Go ahead.
Yeah.
Anike, do you
Yeah,
have
I
a
can
question?
I can have some public questions, I guess.
Okay.
Yeah, very good, very interesting talk. And this is a space which I think is growing, is you see 5 years ago or 10 years ago how this space was, and it's completely changed. And I'm very happy this behavior-based understanding of driving is still important to the industry, and it's hopefully you'll solve these edge cases and some of in going in that general direction. So I noted down a few questions actually, and some of them actually pointed in your thesis as well, and we can come to that later as well. So in your in your chapter for the study-based driving style modeling, you use these MDSI personality factors and pre-crash scenarios, right? And then
Right.
you have all these metrics. One of the metrics I was wondering, what would happen if density changes or other things change? Because that is, I mean, of course, there's a different debate about culture and people driving DC versus Maryland versus Purdue or whatever. But what happened if density changes? Does these behaviors also change in that?
Yeah, so it's really interesting. So in this user study, we basically just fixed all 4 scenarios for the exact same thing to happen, because what we wanted to see was how people reacted to the same things. So we
Right.
didn't want confounding factors. So in this particular user study, we didn't look at density per se, but each scenario had different levels of density. The key idea for each scenario, though, is that we wanted some sort of stressor to pressure a decision to be made. So I will say a limitation of what we looked at, we didn't quite look at density as a variable there, but density is a factor that we've used to kind of pressure users to make decisions. So I would hypothesize that density does play a factor in how people react, because even intuitively, like
You
for
look
my
at more things together, and I see.
yeah. And also, like, if it's too dense, then it kind of limits the decisions that the
Yeah,
human can make. So we wanted to kind of like get the full but again, I think it would be really cool to ablate density to see at what density do users decide that a decision is not worth it, or worth it.
Okay.
So yeah.
I have some other questions I can ask in the private session, but one last question in the general audience is that you mentioned about like this sim to real gap, and I guess this expands on Dinesh's question as well.
Yeah.
Is there any actual quantitative measurement of that gap somewhere, or you just see that there is gap?
Oh, I don't think there is a quantitative measurement in our work, especially because like a lot of the work doesn't quite look at measuring that specific gap. But I do know that, like, for example, this is quite a problem for a lot of the end-to-end driving models that are trained in Carla. So there are new benchmarks like NavSim that try to account for this with like end-to-end driving in the real world. But I know that it's an ongoing research topic, and that a lot of it is kind of like more focused on the perception side rather than the trajectory side.
Right.
But I do know that the sim to real gap between behavior, so if you were to just look at the traffic states and not images, the gap between behavior in traffic, simulated traffic versus real traffic, I think that this is not looked at. And I think this would be like a really great future work to kind of look at, given that we have this paired data in simulation. We just need paired data in real world to kind of measure that.
Because I mean, you're saying that in terms of visual data, the sim to real gap is more, right, than trajectory data. That has traditionally been the case, right? And you're saying that we don't know what happens when it comes to behavioral alignment. So we don't know the features to optimize for to make sure the alignment is better right now. That's an open problem altogether. Okay.
Right.
Right.
And yeah, for visual gap, it's a little harder, also because images are so much more high dimensional than traffic
Correct, yeah.
states. Traffic states could just be a series of positions.
Correct. Yeah.
Yeah.
Okay. All right. No, this is interesting. Behavioral gap is I don't think I've seen any work in that space. I mean,
Yeah.
it's a hard, maybe it's a hard problem anyway, but
Yeah.
thank you. Thanks.
Yeah, I think to measure it, you would need to just begin with, you would need like paired data sets. So like a sim data set and a real data set. So right now we've done the first step and like we've collected a sim data set. But it would be super cool if like we could jump in a car and measure a bunch of people's styles and have them drive through
Right,
different
right.
courses.
I mean, you also need to some metrics, right?
Now we're gonna have to pay, we're gonna have to try to get IRB approved for that, right?
Yeah,
That is true.
Who
That is-
would volunteer to be put in danger?
maybe for sufficient compensation. Someone grads would do it.
It's all about, yes, that is
Yeah. So
100%.
I think once we have that data, like it'll be a really interesting problem.
Yeah.
Yeah, we have tons of like image data, which I think it makes it like easier to explore. But I think images are like so much more high dimensional. I think for behavior, I would think that the gap would be smaller. I wonder if there's even like some transformations we could apply to kind of like make simulated data look realistic.
Like some low dimensional metric to compare, right? In some
Yeah,
sense.
exactly.
I mean, I believe you have a driving style consistency or some in one of the chapters, right?
Yeah,
Some
yeah, I do.
metric. That could be one of the behavior. I don't know if that captures behavior, but I think it does, right?
Yeah, we try to with latent variable modeling, but
Yes.
since it's a latent variable, it's hard to tell like what exactly the latent variable is measuring. We can only like kind of poke at it with like different analysis to see if it's meaningful. So I would say it's too strong of an assumption to say that we've successfully,
Right.
extracted driving style, but I think we're closer
Okay.
in that sense.
Thanks, Sarah.
Cool.
Okay. Any question from the audience? All right, so then we're gonna, sorry, Anike and Dinesh and anyone else online, do you have any other question before we come back to the committee member here?
I'm good.
Oh, good. Okay, great.
Okay.
All right, committee members, any public question?
So,
Yeah.
this fantastic work.
Thank
very
you.
important application. So, I'm wondering how do you quantify how well these simulations match well with the frequency of this kind of edge cases in the. This is my first question. The second one is the driving style based on condition prediction is very interesting. But I'm wondering how sensitive or robust is this kind of driving style based prediction under the domain shift. For example, like the different locations, different driving laws, so on for different contexts.
Right.
How this kind of predictors will work well under different contexts. That's my question.
Okay, cool. So just to repeat, I think the first question, what was it again? It was like on
So
the
how to quantify
right.
how well your simulations match well
Okay.
with the real world.
Right. Okay. So the first question, I'll go over first. So it's how do we quantify that the if I can paraphrase right, that the counterfactual rollouts that we've had in the last work with latent variable modeling, how do we make sure that these outcomes are actually like distributionally like real? And how do we know that, like, for example, like how do we verify this? Because we don't actually have the ground truth of this happening in the real world. And this is like an ongoing research problem. I don't even think people have quite nailed it down in metrics yet. And I think the best thing that we can do is just look at distributional metrics. And a lot of them have to do with kinematics. And so I think for this work, we didn't quite delve into that yet because this is mostly focused on trajectory prediction. But there is like an emerging task called sim agents where they try to measure different kinds of outcomes. But I would say that the sim agents metrics have a limitation in that case, the intent is not fixed. So they're also kind of measuring the distributional realism of intents. So like how likely is this vehicle to turn right or left or go straight? And I would say that our modeling of driving style doesn't quite line up with that kind of distributional realism. So I would say that like currently that's an open problem. There's not really quite metrics with it, but if I were to tackle it, I would look at distributional metrics for now. But that I still don't think distributional metrics would be the entire picture. So I think that that's a tough question, which is also why we have the qualitative results. But I think another useful avenue is to go through like human evaluation. So it would be really cool to see if like, for example, if we could render the first person point of view of this, to have users indicate whether or not this is a realistic driving behavior that they would observe in the real world. And so maybe like, for example, the simulator demo that we had, you might observe that like some of the pre-crash scenarios, it does seem like some of them could occur in the real world. You may have seen someone cut you off. So we would probably conduct like a systematic user study to evaluate like the realism off of humans in that case for the most rigorous. But quantitatively, we could use distributional metrics. And then I think there's a second question, sorry, and just trying to think of the answer. So the second question had to do with
The sensitivity analysis.
oh yeah, right.
Stop.
Right. So to repeat the second question, it was on so if we were to do this on different like under domain shifts or just like basically would the modeling of style change if any conditions of the problem were to also change, like any inputs to the system. And I do think it would change. So this data is this is actually done on Argoverse 2. I don't quite remember which city it was collected in, but I'm pretty sure it's like maybe a city in Germany, something like that. But there are data sets. So I know that the Waymo data set, they probably have the largest open source version available online. And I know for that one, they do have metadata on different, they should have metadata on different types of conditions, but for the perception data set. So there would be some engineering tweaking, I think, that would be done to measure this. But I think it's possible to look at this kind of domain shift. For the purposes of our experiments, we didn't have access to this kind of data to investigate. But we are looking at this in like currently in experiments beyond this work. So what we're working on right now, we're trying to do like these small experiments with like domain shifts in terms of trajectory types. So like is what we learned with straight driving, can it be like, does it generalize to like turning and stuff like that? And we kind of model them as different domains just off of the data that we already have. But I think for more robust modeling, we could use like those larger data sets with metadata and kind of construct, you know, like a source domain, target domain, and see like how this would change. My hypothesis would be that it would change. There's different latent variable modeling just kind of enforces separability within samples. And so there could be different levels of separability across different data sets. 3 might not be the optimal case for all data sets. It could find some spurious factor that is separable by 3. And for example, it could just separate on like traffic light state. So this is also an unanswered question. Yeah.
But I just want to quickly mention that on your question 1 and 2 are in fact coupled. Right. So the differences in the sensitivity of the behaviors really partly depending on 1. Yeah. So that coupling makes the question really difficult, but it's an excellent point. That will be, you know, a natural direction to really look at how sensitive the performances will be subject to the culture shift. And we do know, by the way, there's also the question of verification and validation. All the traffic simulation model, the existing one, has been verified and validated, at least within our research group, prior arts, and also across around the world. I do want to mention that there is a culture differences. Density and velocity are inversely related, right? So when you have very highly dense scenario, the velocity actually goes down, which means that it's actually, you have a different kind of scenario. What was not shown here is the interaction between human and vehicle. And not to mention that we are currently modeling micromobility systems, which is increasingly, Laura is also involved with that, and she didn't say anything about it. Because a couple other students from my class, we've been kind of pursuing that. Is how does a micromobility system actually, which is a meta existence between pedestrians and vehicle, because they have the flexibility of the pedestrian, but then at the same time, they are a vehicle, they are a form of vehicle. So that is interrupting the interesting dynamics that you were asking. Yeah, so it is a really interesting question, and it's in fact an excellent one. That will be a really natural follow-on work for those students who are here.
Yeah, campuses would be a different domain, I think, from like suburban. Yeah.
All right. Mumu? Tom? Public public question from committee member, and then we'll do a close. Okay, all right. Any other question from the audience? Okay, great. And if not, we are now gonna close the session off to the public. We will have a private committee discussion with Laura.
Hey,
Thank you all for coming. And also those online, please log off.
one second.
I think it's only me and Aniket, so it's only committee members.
Okay,
Sorry, can you guys rejoin the Zoom really quick? I just have to end the stream for my long distance attendees. 1 second. Could you
Should
rejoin
we join the same stream? The stream
same
link?
one, same one. I
Okay.
just can't figure out how to end the broadcast.
Okay, sure.